This presentation is entitled Measuring the Behaviour of Pedestrians in High Winds. It's a well-known fact that many high-rise buildings create very uncomfortable wind conditions around their base due to high-level winds being brought down by the face of the building down to ground level. And very often these days on many buildings you'll see canopies such as the one shown here to try to improve the pedestrian environment. As the wind speeds become stronger, however, it can change from being a comfort issue to being a safety issue, where people can be blown around quite dangerously. The little video at the top there, which I believe is from the University of Eindhoven, and for which I have to say thank you to Professor Blocken, shows that it's not just our species that are affected by high ground level winds. A number of criteria exist for assessing whether winds at ground level are comfortable or dangerous. These usually take the form shown in this table, which shows a couple of UK practice guidelines. We have a mean wind speed that mustn't be exceeded for 1% of the time, say, for a particular type of activity. Most of those activities there are relevant to the comfort situation. The bottom row, however, is more relevant to what we'll call the distress situation, the safety considerations. And they aren't, it has to be said, terribly well defined. They're largely based on subjective questionnaire data from several decades ago in different parts of the world. Now, in the middle of the 2010s, a large building was built in Leeds called Bridgewater Place, and this was found to have unacceptably high level winds around its base that caused significant danger to pedestrians and indeed to vehicles passing by. And one of these vehicles blew over and killed a pedestrian. An inquest was therefore held, and the coroner, Melanie Williamson, the Wakefield coroner, was concerned that there might be corporate manslaughter charges arising from the first inquest, so she actually adjourned it. These charges weren't brought, but at the second inquest, she made some very severe recommendations about wind speed closure levels for that particular road around the base of the building. Partly because of this incident, the University of Birmingham were awarded a sizable research grant by the Engineering and Physical Sciences Research Council to look at the safety of pedestrians, cyclists, and motor vehicles in highly turbulent urban wind flows. And this involved full-scale experiments of wind conditions on the university campus. It involved wind tunnel measurements to try to replicate these conditions. It involved CFD calculations of various types, and it involved actual measurements of pedestrian and cyclist behaviour in high winds. And it's with the last of these that this particular presentation is concerned, pedestrian and cyclist measurements in high winds. We actually made measurements of pedestrians and cyclists walking or riding along a track at the base of a very large slab building. The building on the left there is the Biosciences building. And we installed anemometers along that track to measure the wind speed relative to the pedestrians. It's the pedestrians I'll be talking about here rather than the cyclists. We also had a reference anemometer at the top of the Muirhead Tower, which we can see on the right there, to measure the high-level reference wind speeds. Now, to terribly misquote Jane Austen, it is a truth universally acknowledged that when wind engineers try to make full-scale wind measurements, the wind ceases to blow. And that indeed was to an extent the case for the measurements that I'm going to describe here. During the 2 years of the measurements, we only really had 2 storms that we could use where the winds were strong enough, or that it was possible to get our group of about 20 volunteers into place to take advantage of them. For the measurements we made, we used shoe-mounted sensors for gait measurements. We mounted small sensors that included inbuilt data loggers and batteries onto both the left and the right-hand feet. And we also mounted accelerometers on the body of the volunteers that we used on the back of them. Again, they contained accelerometers and small data loggers. So we were able to measure the actual response of pedestrians to high winds. As I said, we had 2 trials, and most of the time in these trials, the wind was from the southwesterly direction, the prevailing wind direction, and gust speeds were up to about 17 or 18 meters a second. They were stronger in the first of these trials, which was quite a sizable storm, named Storm Ophelia. And if you look at the wind speeds for that storm in 2017, the red arrow on the right shows the wind speeds that were measured at the top of the Muirhead Tower, and they can be seen to be fairly steady. The ground level wind speeds, however, are highly variable. And that, I think, needs to be borne in mind. So this figure shows a histogram of the gusts that were experienced by our group of volunteers. As I said, there are about 20 of them over a wide age range of both male and female. And we can see that the gusts we measured go up to 18 meters a second, but there are only a very small number of gusts in the top speed range, which was not altogether satisfactory, of course. If we look at a response in a typical gust, what we show here are the wind conditions in the top 2 figures, the distance along the route as the volunteer walked along the route from 0 to 63 meters. And the top left-hand figure shows the gust wind speed experienced by the pedestrian. The top right-hand figure shows the wind direction. The bottom figure shows the outcome from the back-mounted accelerometers. The top line shows the vertical acceleration measured in gravity, and that is about 1, and it shows a bit of a response as the pedestrian walks through the gust. The bottom figure is the lateral acceleration, and that's measured about 0, of course, and that shows a slightly higher response. If we look at the results of the gait measurements, we don't see very much for most parameters. Again, I show the wind velocity and the wind direction in the top 2 figures. Then the gait cycle time, effectively the time of a step, the stride length, and the stride speed. And again, you can't really pick out the wind gust as the pedestrian passes through it. If you look at the parameter known as the swing width, however, and it's shown there, as indeed all of these are for the left hand and the right hand feet, you can see perhaps in the swing width, which is the lateral movement of the feet during each stride, you can perhaps pick out some sort of response as the pedestrian goes through the gust. This is a little clearer if you plot the gradient of swing width against the wind velocity here along the route, and you can see as you go through the gust, you get some quite high gradients. However, the data is very, very scattered. In fact, it changes from one volunteer to another volunteer, and even for the same volunteer, it can be very different from one pass along the route to the next pass along the route. And this is, of course, due to the variability in wind conditions, also, of course, due to the variability in human response. If we go to rather higher level wind conditions, though, we do begin to pick out instability responses here. And here you can see one of the volunteers in the trial, a postdoc in the group, becoming unstable for a short while as he walks through the gust there. And if we now plot the output from that particular run, we can see the gust velocity is very clear. It goes up to 15 meters a second, a rather smaller gust at the far end of the route with some variability in wind direction. And here we can see a rather greater vertical and horizontal acceleration. If we look at the gait parameters from the foot measurements, here most of them begin to show something, some sort of response as the volunteer went through the gust, particularly the large gust at the start. The swing width response is actually becoming quite significant. And if again we plot the swing width gradient and wind velocity along the length, we can begin to pick out quite significant effects. But again, there is much variability, much variation from volunteer to volunteer, from one pass to another pass. All a bit subjective. We can do a little more quantitative analysis, however, if we take the entire data set. And if we look at the entire data set, we can begin to pick out three sorts of response. And I've called these responses the swing width response, the acceleration response, and the instability response. The swing width response is when the swing width gradient exceeds a specific value. And you can see these swing width responses kick in at very low wind speeds, very low gust speeds. And in fact, they're mostly unconscious responses on the part of the volunteer. They don't know they're responding, but we can measure them. And they occur for something like 40 to 50 to 60% of the time at gust speeds of less than 10 meters a second, and then increase rapidly. So for gust speeds above 40 meters a second, they are always present. Acceleration responses are based on the lateral acceleration. And when this exceeds a specified value, we can see that the acceleration response begins to increase at about 10 meters a second. So by 60 meters a second gust speed, then 100% of the events have a significant acceleration response. At the highest gust speeds, we get something like we've just seen in the video, an instability response beginning to come in at 14 or 15 meters a second. However, it needs to be borne in mind that we've got very few gusts in the upper bands of gust speed there. So what can we conclude? Well, I think we can define three types of pedestrian response to strong winds: a gait swing width response, a body acceleration response, and an instability response. Frustratingly, though, the sample size was small. The experiments were inevitably restricted in scope. But be that as it may, I think the results that we show here are interesting. They're indicative of what can be done, and they potentially offer a more quantitative way of determining safe wind speeds than the current, perhaps somewhat ad hoc methods. Thank you very much for listening.